Yeah. Good afternoon, all of you. My screen is visible. Hello. Hello.
Yes,
Yes,
sir.
sir, your screen is visible.
Yeah. Fine. Okay. Today we'll see that design of tuned filter. As we discussed in the previous class, there is a different types of filter. The two single tune filter, double tune filter, high pass filter, C type filter, all these things is a brief note, and then we'll move on to design of a minimum cost tuned filter. So here is a cost is one aspect to get the minimum cost we are designing as a filter. So in this filter cost is in terms of the requirement of the reactive power. So that is only the concept, because why we are using filter? Because of harmonic. Once the harmonic injected in the lines, there is a lot of disturbance is there, that also we discussed in the previous class. To overcome that, and also one advantage of designing a filter is here that this filter will supply some of the reactive power. Whatever the reactive power required by the system, some portion of that this filter is going to supply. The rest of that, other component like a capacitor, banks, all these things, synchronous condenser. So that will supply the reactive power. So that is the reason here we can see that to get the minimum cost based on the reactive power requirement, we will see that AC filters are used for filtering the reactive power compensation. So there is a filtering as well as the reactive power compensation, but not total reactive power compensation. Only some portion of reactive power is going to compensate. So that is the thing here. That's what I mentioned. It's not, but even though I mentioned as a reactive power compensation, but not total reactive power, it is some portion only. The capital cost of AC filters varies between 5 to 12% of the capital cost of the HVDC terminal substation equipment. So this also has a major role in that HVDC substation, in that only some reasonable amount it is going to be contribute. So the cost is involved in a substation in terms of the filters, because not only one filter, many number. I will show end of this class. There is a substation. It may consist of many number of protective devices and also filters, all these things, and that will be there is up to 5 to 12% of the total substation cost. It will be involved in this, and total reactive power generated by the AC harmonics filters is normally 10 to 40% of the active power transfer of a HVDC link. So there is a total reactive power generated by the AC harmonics. This will be the filters is normally 10 to 40% of the active power transfer. So the remaining, and that means whatever it is required, in that it will be supplied this much amount, and the remaining reactive power demand that will be fulfilled by the shunt capacitors or synchronous condensers, all these things. That's why initially the first line itself I mentioned, it is not completely reactive power compensation. It is only the some portion of the reactive power is going to be compensated. And the rest will be the synchronous condensers are used on the AC side of HVDC link when the short circuit level at the AC bus due to AC network is less than required. Total capacity capital cost of a AC harmonic filter include the sum of the components. So because while you are discussing as a minimum cost, so what are the costs involved in that? We'll see first. And in that there is a three costs involved in that. One is a cost of a AC filter capacitor, because in our tuned filter, maybe in the previous lecture we observed that there is a L and C in series with the resistor. That is only the single tuned filter, and double tune also there. Rather than using two single tuned filters, you can use directly as a double tuned filter as well. But in the cost aspect, in a tuned filter, one is a capacitors. That is a cost of capacitors, which is directly proportional to the reactive power, that is MVR size of the AC filter branch. So what is the capacitor is going to supply the reactive power, based on that the cost is involved. That we call it as a QC, means capacitor reactive power, MVR. And another cost is a there is a reactor, that is a inductors. We can see that cost of AC filter reactor, which varies inversely proportional. So that is inversely with the MVR size of the filter. And third one, there is other cost. We can say that circuit breakers, and then CTs, PTs, like that, resistors, bus bars, all other equipment, that we call it as a constant cost, or you can say that resistance also we can consider, or otherwise in general word you can say that constant cost. So these are the total three costs are involved in a tuned filter. Now total cost I am expressing K, I consider as a K. I will at moment there is a empirical relation like that, directly I am telling, but I will design after this slides. I will show how this expression we got it. So what is the K cost, total cost I am considering, that is equal to AS plus B by S plus C. That means AS component is a capacitive cost, and B by S component is a inductive cost, and C is a resistive cost, or you can say that constant parameters. So how this expression is achieved, I will show at the after the derivation of this, because in some cases the question may be a full essay question. At that moment you have to derive what is the starting point onwards, means getting AS into plus B by S plus C, how you got that, that also we have to derive. Otherwise you can start here. If it is part A question, something like that, let it be essay question that they divide in two parts, A and B. So if it is small question, you can directly start here. That is the reason I am mentioning direct expression. Total cost is equal to AS plus B by S plus C. But I will later I will derive how you got this also. At moment ABC are the constant, S is a MVR supplied by the filters. So that's what you can see. The capacitor is proportionate and the reactor is inversely proportionate. We mentioned in the three statement previous slide. Based on that, AS plus B by S plus C. And now what is our requirement? Minimum cost. So we will get the minimum value. If any equation is there, to get it as a minimum value, what we want is differentiate and equate it to 0. So here the parameter is S, and differentiate with respect to S and equate it to 0, then I got it what is the S is equal to. So from this expression you can see that A and plus B by S is nothing but a 1 by X notation. Then I can write minus 1 by X square into B. So that means minus 1 by S square, and C is mentioned as a constant. So differentiation of constant is 0. So from this S is equal to root B by A. And now, so minimum cost is we got something S value. So you substitute in this equation whatever you derived the S value here, this value S you can substitute in this equation. So wherever S is there, you can replace this by root of B by A. And now what I can get, K minimum, that is equal to A into S. S is root B by A plus B by S. So by S in the sense that will become as A by B plus C. So if we simplify this, I got it K minimum is equal to 2 root AB plus C. And now MVR rating of the capacitor in tune, H is the order of that harmonic, is sum of the fundamental component MVR. So this is the final expression is this one only. If they ask the small question, you can just start here and find the derivation part. The K minimum is equal to 2 root AB plus C is a constant value. So you can stop at this point also if it is a small. Otherwise, I will derive what is this expression onwards, and again I will do the differentiation and equate it to 0. We will get it in the sequence. So now here the sum of the fundamental component MVR and the H order harmonic component also we can consider. The cost of the capacitor is assumed to be directly proportional to the MVR rating. So in the previous 3 points I mentioned, the cost of the capacitor is directly proportional to the MVR rating, and inductor is inverse of that. Like that, we can find the total cost. You can see the total MVR rating of a tuned filter is sum of the MVR rating due to fundamental and then voltage source V1 and MVR rating due to the harmonic current of H order filter. So now in this Q is a reactive power, total MVR rating of the capacitor per phase, because just we in the normal system there is a 3-phase system, we can just derive the any phase that will be applicable for the rest of the phases also. So now according to this statement, the sum is equal to the fundamental plus order of the harmonic. You can see that Q1 plus Qn. So what is the Q1 fundamental quantity? So that is the capacitor. So I can represent I1 square XC. So this I1 square XC also I can write, otherwise there is a V1 square by XC. Anything is same, either I1 current, just I square R or V square by R, something like that. No? So I1 square XC or V1 square by XC. And what is this factor? This is equal to I1 square XC2. So that I can represent in the denominator, because I made it same as I in the numerator. The XC if I write in the denominator, so I can write the order of the harmonic H and WC. So this is the total MVR rating of a capacitor. I am not considering rest of the terms, that also will come into the picture. First term I consider as a capacitor, this one. But later, once if you get the generalized expression of a capacitor, then you can easily make it as a L, because it is inversely proportionate, we mentioned already. So therefore, similarly inductor is equal to, I can write directly. So at this moment I consider QRC, that is a MVR rating required for the capacitor, what we call it as tuned filter contribution of the capacitor. So then you can see that V1 square W1C or omega, not a W. So omega 1C plus I1 or I square, that is a harmonic order, divided by H omega 1C. And now we can see that just for simplicity I consider S is equal to V1 square omega 1C, and this factor you can see as such I mentioned H square by H omega 1C. And now where S is a size of capacitor, we already mentioned it is a MVR required by that. So size of the capacitor I can represent V1 square omega 1C, just replacement of that equation only. Omega 1 is a fundamental frequency, V1 is a fundamental voltage of AC network, and IHF harmonic current. So I represent the current and H is a harmonic order. That is what order we can replace it later. I want to reduce our harmonic quantity or 5th order or 7th order or 11th order, depends. Suppose in any specific converter, based on the pulse number, lower order is going to modify, no? So if I use 6 pulse converter, you can start the lower order is different, and 12th pulse converter, it will come from 11 and 13th onwards like that. So the based on your requirement, you can able to suppress your harmonic by designing this filter. At that moment, I want to design only some 11th order harmonic, let us assume that. Then the H becomes as 11th order. So that is only the order of the filter. So now we can simplify the second term I am writing. The first term as usual S I can keep. What is the second term is I square by H omega C. Just simplification I am going to do in terms of S quantity, that is the size of the capacitor. So what we can do is you can see the first factor V1 square omega 1C by V1 square omega 1C, it won't affect anything because this will get cancelled. So whatever I am representing, the second term, that we can retain as such. But now for our simplification, you can see that what will happen, V1 square H, I square HF, this term and this term divided, you can see that this factor and this factor I keep as such. And what is the left out of S, wherever I want to write S, I can write V1 square omega 1C. So there is a V1 square omega 1C. I can write as a S. This denominator I can write as a S for replacing of this. The whatever left one, omega 1C is there, is that will get cancelled out in the numerator. Omega 1C cancelled out. So what is the denominator? Only H is there. So you can represent SH. And numerator, remaining portion I represented as a numerator. So V1 square I HF square. So by SH. So this is the second factor alone. And now you can write directly QRC is equal to S plus V1 square I square by SH. And that is the portion you can see here. This very small simplification, I divide the numerator and denominator in the same factor. So anyhow the second factor retain as such because these two will get cancelled out. So that is just for simplicity of size of the capacitor. We will get in terms of the size of the capacitor. So this is the QR case. That means QRC is represented as MBR supplied by that capacitor in terms of the size of the capacitor we mentioned. Similarly, what is the rest of the portion is the inductor. That I can write same fashion, QRC is replaced by QRL. What is the difference already mentioned, though the cost is directly proportional to the size of the capacitor, whereas here is inversely proportional to that. So that's why S by H square, and this will be the second factor. So you can just sum that two things, assuming the unit cost of capacitor and reactor to be directly proportional to the respective MVR rating. So now you know capacitor and you know the inductor, so just you can add the two things and with some constant, so you'll get it as a cost. So okay, what we want is here in terms of the cost. How will you get the cost? This is the MVR rating of the capacitor as well as the inductor. So now you just cost, if I call it as a sum factor, so K into QRC, because the K is unit. So based on your requirement, that may be term or MVR rating 2 times or 3 times or whatever you can make it. So this is the cost of capacitor, and similarly this is the cost of a reactor. The cost of resistance is a constant. So that's why you don't need to add this factor. Finally, you simply can add some C, or you can say that it is a constant value cost of a resistor. Now we have individually cost of the capacitor as well as the cost of the reactor, and now you can add other term is a resistor term. So that's the reason you can mention here the cost is already stated in the first statement, rupees per MVAR. So reactive requirement. So based on, because obviously if MVR requirement is more, the cost of the capacitor are more, because size of the capacitor will be more. then size of the capacitor is more, that is directly proportional to the cost, like that. So that is the terminology here. So you can see that total cost K, cost of the capacitor, cost of the reactor, cost of the resistor. So now in the previous slide we know what is the cost of resistor, cost of capacitor, cost of reactor, cost of the resistor. Add these three, we will get it as a K. So now I added that. So what we can get, Kc into QRC plus KL into QRL plus KR. KR indicate that there is a resistor value. So substitute this QRC, QRL values already there in the previous slide. You can see that this is one equation and this one is another term, that is a QRC S plus V1 square I square by SH, and QL is S by H square plus V1 square I square by SH. So just these two terms you can substitute here. Then what I can get, total K, that is equal to this term, I call it as a K into QRC, and this term we can represent K into QRL. Then the last term I call it as a constant, is a resistor value. And now only simplification, nothing is there, it is very simple simplification. What I did is this Kc I multiplied inside, and KL also I multiplied inside, and I am taking S common. You can see here I am taken S common. What about remaining term Kc, and here you can see S is common I taken, and then KL by H square, and here I am taking from these two factors I taken as 1 by S is common. So if I just remove the 1 by S outside, the rest of the terms. So now what is this? S into something plus 1 by S into something plus KR. What is KR? It is a cost of the resistor. So now we can see that KR will give the cost of the resistor, and the previous term you can see now it is equivalent to that of a K notation on S into A plus 1 by S into B plus C. You can represent it initially, no, K, that is equal to AS plus B by S plus C. This only I started initially. So now how you got this is this one expression. So that is the reason, depends on your question. You can see I am audible, no? Hello? Anybody?
Yes, sir.
Yeah, fine. So total cost, this expression I started, and the question is, here is a minimum cost of the tuned filter. That's why to get minimum value, what is the S? That is because size. S is what? S I mentioned as a size of the capacitor. So what is the size you have to use to get it as a minimum cost of a tuned filter? That is the reason we differentiate with respect to S and equate it to 0. So that is the previous slide, in the starting slide I mentioned. No? Now this equation where A is equal to this parameter and B is this one and C is nothing but a say. Either you can use in terms of Kc, Kl, Kr, anything, or ABC. Any notation you can follow, both is same. And now what I got is K is equal to AS as per the previous initial starting point, AS plus B by S plus KR. So this is our K. S is a size and K is the total cost of a filter. So now to get minimum cost, as usual, you just differentiate and equate it to 0, and finally same thing, S minimum is equal to root B by A. This S minimum you can substitute it in the K equation in the previous slide, that is equal to AS plus B by S, like that you can get it as a, this is a B by S plus C. So you just put it wherever S is there, that become as a root of B by A, that will give as a K min. So K min will get it directly, that will get this expression. K min is equal to this one, and from this you can just substitute what is S minimum. because K minimum is nothing but a S minimum only. The size is proportional to cost, no? So S minimum already derived root of B by A. And simplification if you do, you will get it as a K min is equal to this one. Same as the previous expression. Only thing is we can say that cost of the resistor is a constant. So you can add that parameter here, or directly you can consider K minimum cost is equal to 2 root B by A. So what is the A value and what is the B value? You know that from this previous. This one is A and this one is a B. Now we can see what is the value, order of harmonic, all these things will involved in that. And for that particular order of harmonic, you can easily identify what is the minimum cost of the filter. So this with the different curves, size of the MVR per phase. So this one with respect to the cost of the filter, if you plot now comparatively, you can see that this is a minimum cost of the filter. So this level will give as a minimum. This is the fundamental and this is harmonic component. And finally, if I add that thing, we'll get it as a minimum cost of the filter. So this is the point wherever the lowest point, that is our optimal value of the filter, or you can say that minimum cost of the filter. So that is one of the important question they asked that design single tune filter. Just previous class I designed already in the some mathematical modeling, and if they ask the cost wise also, you can use this formula. And there is another filter is a double tune filter. As you are aware that tuned filter is used to filter out any of the specific harmonic, whatever may be the order of the harmonic. In the particular order of the harmonic is going to be removed. So that we call it as a single tune filter is some particular frequency of this filter. Another one is a double tune filter. In double tune filter, we can see that two order is going to be removed. So either you can use directly to single tune also. If I use two single tune, little bit loss will be more and cost, all these things involved. That's why in general, or one thing in transformer case also, for three-phase transformer, let's consider what we are doing. There is a two options. Either single unit of three-phase transformer also you can use it, or three single-phase transformer you can use to form as a three-phase transformer. They have their own advantages and disadvantages, all these things aspect like that. Either you can use two single tune filters or directly as a double tune filter. So you can see that this filter out two discrete frequency instead of using two single tune filter, you can use directly as a double tune filter, and its power loss is going to be reduced, because instead of using two, if you use any one, the power loss is going to be reduced. So and other same thing, advantages. Only one inductance is subjected to full line impedance voltage, and power loss at the fundamental frequency is considerably reduces. That's what in the first statement also power loss will be made this. And this is we can use as a double tune filter, and these two frequencies is going to be suppressed by using as a double tune filter. And high pass filter, there is some empirical relations are used here directly. What we have is a high pass filter out the harmonic of a higher frequency. So whenever if you want to filter out the higher frequencies, obviously that is a higher order, you can say that very higher order into 50 will multiply, that leads as a higher frequency. And the design some relations are given in the normal, it is not the step-by-step relation, it is only the empirical relation they mention. We can filter out, eliminating the harmonics of the other than 17 order. So I already mentioned very high frequencies it is going to be removed, but high frequencies in the sense order of the harmonic is high only, we will get it as a high frequency harmonic. So because into multiplied with 50, that is the order of the frequency, and this is the diagram will represent as a high frequency based on your design value of RLC, that is a design component. That particular order is going to be eliminated. So Z naught is equal to root C by L, and sigma is R by Z naught, and H naught is equal to 1 by root LC. So some empirical relations they mention. You can choose that sigma value 0.522 and H naught is root 2 into H minimum. But all these relations by filtering some of the order of the harmonic by tuning the parameters such a way that they concluded finally if you select 0.5 to 2 in between, you will get it as a better performance in that design component. H minimum is the smallest of H2B handled by the filter. So whatever the higher order harmonic, in that many order will be there. Which order you want to consider, you make use of that. And filter impedance ZHF is given this expression, and another one is a reactive power supplied by the filter. And yes, already we noted in the previous, this is the size of the filter. So this much reactive power supplied by the filter, so then only compensation is going to be takes place. All these efforts, the compensation of reactive power also involved in this, it is a harmonic. So how much it is going to be compensate, so that is the reactive power supplied by the filter. And some components inside depends on your capacitive in nature or inductive in nature. If it is a capacitive, it will be supplied, or inductive, it is going to be absorbed. So that is all, there is a SVC or any fax components, you can use it, StatCom you can use it, and UPFC, that is a compensation. That is entirely different subject in fax. You can take it as a simulation experiment also. What you will do is just what you call it as, you take it as a transmission line from source, and then some transmission line 10 kilometers or something impedance you can take it, and the load side you connect some reactive power, some inductance and then capacitance. And now see that you just connect power meter. There is a voltage one input, current is another input. You see that what is the power, real power and reactive power. Same side, in the load side also you measure voltage, load voltage and then load current. Connect one power meter, that like reactive power, real power. There is a simulation black power meter is there. You give inputs voltage and current, and output will give as a what you call it as real and reactive power. Now see that without compensation, you load something, you can give some source, 3-phase or a single phase, anything. What is the source real power and reactive power? What is the load real power and reactive power? So only the problem will arise in the reactive power. It may not be the same based on your load. Suppose if you see that resistive load and all, it won't be happen anything. But if you use as a inductive load, so what we need to compensate, whether I need to generate the reactive power to compensate, or I need to absorb the reactive power to compensate. For that, that is actual system. In a power system, there is a source and there is a load, in between there is a transmission line. If you want, in the next class and all, I will show that also, how you have to compensate. Then you design your compensator. What is the compensator? Either you go for SVC, you can go, and or you can see that StatCom you can use it, or you can use UPFC, anything. There also you can use simulation diagram. As you are aware that just for simplicity, SVC, if you consider, there is a fixed capacitor and TCR, that is anti-parallel thyristor with reactor, and you connect that is a in between source and load. You connect there is a SVC in between source and load. Now you tune the SVC such a way that it has to compensate. Now depends on your load requirement, or you can say that what is the load. Let's consider load is fixed one, and you may compensate the reactive power. Suppose you need to supply more reactive power to compensate, then you tune SVC to supply it. Or some cases you need to absorb the reactive, because load is released suddenly, the reactive power will increase. So you have to compensate. So somebody has to absorb that. So then what will happen? SVC has to absorb that. Either it has to generate based on, because fixed capacitor is there. Current passing through the TCR will compensate that. So automatically you can able to either in the observed mode or in the generating mode, finally it is going to be compensated like that. Or else you can go for StatCom also or UPQC also. You just design based on your what you call it as reactive power compensation. There is a lot of reference papers also there. If you want, you can do it. And later, if time permits, some of any simulation HVDC transmission system, how it can work, will show. I will show some of the simulation diagrams also after completion of the syllabus. It may be take only 2 more or maximum 3 hours and even 15 it. It is only multi-terminal DC system. They mention only the syllabus for the multi-terminal DC system only for applications, advantages, series connection and parallel connection comparison. So only very few topics they mention in a syllabus. It will take only 1 or 2 hours. So there is a types of MTDC, that is multi-terminal, and series connection and parallel connection, comparison of series and parallel, and control of a MTDC. Only very small topics is mentioned. It will take only 2 hours to complete that. Very small thing. So that's why after completing that, still I think 1 more week, maybe 2 or 3 classes are there. I will show the simulation and you practice that and you try to add some of the fax controllers to compensate all these things, and you can just prepare one conference paper, something you can somewhere give the seminar in any of the international conference and all. Like a practice, you do such a way that you will get the more familiar in the either in any of the topic, not only in HVDC or a fax controller, or maybe in power electronics side or in power system load flow side. So such practice is required to do your project, or any internship also you require that, because that is the reason we introduced the simulation techniques of electrical engineering in the elective course, because for MATLAB programming purpose and all. So that you can see in the next few of the classes. And now you can show that the filter improves if S is injected and higher values of H0 can be chosen. Therefore, in advantages of designing of a 12 pulse operations. And now you can see that the protection of filters. So generally there is a protection of filters is exposed to its switching action, whether it is in on the state or off state and all. So complete depends upon the magnitude for its short circuit ratio and the saturation of performance converter transformer. So during on, let it be as a switching on condition, filter current can completely depends upon the magnitude ranging from 10 to 100 times of the harmonic current. And similarly, lower range magnitude is applicable to single tuned filters, and high range value is applicable to high pass filters. To limit the higher overcurrent values must be designed on the reactor coils. And during switching action, that is off condition, the capacitor remains to charged values with voltage at the switching instant. And in order to avoid this, it must be discharged from a capacitor by making short circuit devices through converter transformers, or maybe in the loading its resistors also it is going to be dissipated. And in AC filter, if its network frequency deviates the nominal values, it will be results in higher current and losses. If these exceeds the limit, filters will be disconnected. So this is just only for protection. Now, as you are aware that AC filters is discussed for single tune, multi-tune, high pass and all, but DC filters normally will be required in the multi-terminal DC system, not in the 2-point DC system. Whatever so far we discussed, it is a 2-point DC system. Preferably it will be isolated in even circuit breakers, or you discussed in the DC circuit breakers also not required in the 2-point HVDC system, like a sending end, rectifier station, transmission, and then inverter station. There DC circuit breakers and all not required. And now in the case of filters, DC voltage across the converter contain both characteristics as well as the non-character. Other than characteristics we call it as a non-characteristic. So due to reasons I mentioned, no, due to that they may get it as a non-characteristic harmonics also. These harmonic results in the DC line and causes noise in telephone circuits. And the harmonic current varies with the distance of harmonic voltage source at the converter. Smoothing reactor in the DC filters can be generated along its line, and the effectiveness of the DC filters is the following criteria. You can see that telephone interference factor, and then induced noise voltage in millivolts per centimeter in parallel test in away from HVDC line will be maximum. In telephone lines which close to HVDC lines will be maximum permissible noise. And this is the total, some basic converter station. I think I may be shown in the previous of any of the class also. There is you can see that 12 pulse converter, there is 6 pulse converter, another 6 pulse converter, star, and then delta star, all these things. I think one thing I need to mention you, there is a slip test 2 is there. When in next Monday, there is a slip test 2. The time may be at 5 o'clock or 6 o'clock. I will mention you the later. In the LMS, I will submit. You just write that slip test 2. The syllabus for that is a 4th unit. I mean, this unit only. And multiple choice bits are available in Kanchandana book also, in HVDC transmission. I think I already shared you somebody through mail or something. If you want anybody, you just share me the mail ID. I will attach that soft copy. And for your total syllabus is going to cover in Kimbark one book, and then Padiyar and Kanchandani. Only Kamakshaya, not Kanchandani. So Kamakshaya. So these 3 books are sufficient. Maximum syllabus is covered in Kimbark. I will share all these books. I already shared you, I think so. If not, anybody can mail me or message me that your mail ID. I will attach these 3 textbook. You can share it. And this is the actual structure. There is a single tuned filters, and then DC reactor, and then earth, all these things, arresters. So a lot of protection circuits are there. I mentioned here filters. It's consisting of LC components which passes the frequencies within its pass band and stop remaining frequencies. That is the filter. And AC filters is designed to reduce the harmonic current into the AC system. And DC filters, DC reactors and DC surge capacitors serves main function is to reducing voltage or current ripple on a DC line. And smoothing reactor, just I given one small sentence because all these topics are in detail is covered in the previous, so it is like a summary. Smoothing reactor, a smoothing reactor is placed in series with the converter unit to reduce the current transients. And DC damping circuit, it consisting of RNC connected between the DC poles bus and the stationer, which is used to reduce the voltage transient. And DC surge capacitor connected between DC line and stationer to reduce the amplitude and stiffness of lightning surge appearing along the HVDC pole. And the resonance circuit is said to be resonance when the applied voltage V and the resulting current I are in phase. At the resonance frequency, circuit impedance is low. And tuning of a filter to achieve desired performance, adjust the LC parameter of a filter to some specific frequency. So that's what single tune, multi tune, all these things is just specify that based on you can design the values. And size of the filter. Size of the filter is directly proportional to the reactive power. So that is also mentioned. And double tune filter, it will be filter out to discrete frequencies rather than using as a two single tune filter. Second order high pass filter designed to filter out the higher order harmonics. Tuning of the filter are simple. losses of filter can be reduced using C-type filter. And small problem designing of minimum cost filter, we can see that components of minimum cost of fifth harmonic tuned filter. So what is it means is I need to find the capacitor value, inductor value, all these things, and you need to design that. What order I want to suppress is fifth order harmonic. That is a 6 pulse converter and rated for plus or minus 100 kV, that is a pole. You can say that positive pole and negative pole, and 500 amperes, and a DC side filter are to be connected to 230 kV 50Hz 3-phase line feeding DC line through the 6 pulse converter. And voltage, I mentioned no, the can see the capacitor as well as inductor, all these things. So that will be 200 rupees per kVR, not MVR, because based on our requirement. Can see the cost is mentioned 200 rupees per kVR and 400 rupees per kVR in the inductor side, and capacitor side is 200. And the input power factor is mentioned 0.866. So now that is the question what we derived so far in the previous single tune filter, only that formulas you can substitute here. And now DC power bipolar line, they mention as a plus or minus 100 kV, and now net power is you can say that mention in the data, you can see that there is a 6 pulse converter and there is a 200 kV and 500 amperes current. You can mention, because it is a bipolar side, there is 100 plus or minus 100 kV is mentioned. So, and then the volt current is given as a 500 amperes current, then the power will give as a 100 megawatt. And assume no loss in a converter, and input to the link AC system is mentioned now 100 megawatt. We got it as a 100 megawatt. Now AC current fundamental and fifth order. So we need this. So fundamental, you can see that power divided by root 3 VL into cos phi. Cos phi is mentioned as a 0.866. So therefore power is 100 megawatt power. So 100 into 10 power 6 by root 3. Voltage is connected to the source. They mention 235 kV and I mentioned 235, and power factor is 0.86. So we will get it as a current, AC current, fundamental AC current, we got it. That I can represent as I1. You want to can mention here is a I1. Another one is I want to suppress this fifth harmonic current. So you can find fifth harmonic current I1 by 5. We will get it as a 56.6 amperes of the current. And now per phase voltage 235 divided by root 3, that will give per phase, and the A value is known, B value is known, minimum cost is expressions we already derived in the previous A value and B value we see plus VL by H square, and B is V1 square by I square by H. This expressions already in the previous derivation is there. If we substitute that, we'll get it as A value is this one, B value is this one. So size, what is the S minimum? This is a minimum cost of the filter we need as a optimal size of the capacitor. So our filter size. So now you can see that S minimum, we'll get it as a B by a root. So we'll get it as a 5.73 MVAR is required per phase to get it as a minimum cost. And then cost is already derived K minimum, that is 2 into root AB. We will get it as a cost of that will be here. And the design part is L and C is already required. They mention the components of tuned filter for the fifth order harmonic, and C is equal to H minimum by V1 square omega 1, and L is equal to this formula. And now we have to use 1 microfarad of C, and L is a 0.405. So this is our components C and L. Now R is depends on your something cost also you can add it, resistor value, it is very minute, even you can neglect, but even you can add the cost, you can add this is for C term, that is the cost of the resistor. So this is one important problem, design of the filter. So now another one you can see that series resistance, because R is not at design, no, in the previously. Cost also not involved. So that's why by make use of the Q is equal to X by R formula, but assume the Q is 50 and R is equal to omega L by Q, then we'll get it as a 12.75 ohms is our R value. And capacitor is the part of the filter, and fifth harmonic will also supply some reactive power at the fundamental frequency. So that you can easily calculate by using formula. Let it be Q is equal to P into tan phi. Tan phi is a cos power factor. Cos phi is known, no? Then phi is equal to cos inverse of that will give as a phi here. So then P is a power. Then you will get it as a this much reactive power. The who will supply this? This will supply by the filter. The rest maybe depends on our requirement. Other components is going to be supplied. So this is the complete design of a filter. So this is the end of your fourth unit, and I mentioned no in the next Monday is a slip test 2, and I also give some assignment questions overall from third unit, fourth unit, fifth unit, and 2 questions I will give. That also you can write and submit it in LMS. That is complete your internal portion. What you call it as mid 1, mid 2, and then 2 slip tests as well as 2 assignments. So based on that we will select. So this is your end of today's class, and you give your attendance and you can leave.